Okay, so that is the general idea of how to solve recurrence relations using characteristic equation. And let's see this on an example. Here we have a linear constant coefficient homogeneous recurrence relation with degree 3. Tn equals Tn minus 1 plus 4 times Tn minus 2 minus 4 times Tn minus 3. And obviously, since this is a degree 3 recurrence relation, we have 3 initial conditions. Okay, so the first thing you need to write is the characteristic equation, which is obviously r to the power 3 minus r squared minus 4r plus 4 equals 0. At this point, you have to solve this. I mean, if it's an easy equation, you can do it by hand. If it's not, if it's a higher order equation, etc., you can use computing tools. In this case, it's a little bit easier. You can factor it out and see that the solution or the roots to the characteristic equation is 2, minus 2, and 1. Okay, so we have 3 distinct roots. Therefore, the solution is going to be of the form some constant times 2 to power n plus some constant times minus 2 to power n plus another constant times 1 to n. So 1 to n is already 1. You don't even need to write this. And how are we going to determine the coefficients k1, k2, k3? Of course, using the initial conditions. Just apply P0. So set n equals 0 in this expression. What you get is k1, because 2 to power 0 is 1, minus 2 to power 0 is 1, 1 to power 0 is already 1. So k1 plus k2 plus k3 is 6. And then set n equals 1, which gives you 2 to power 1 is 2, so 2k1. Minus 2 to power 1 is minus 2, so minus 2k2. And, well, this is already 1. Plus k3 equals 5. 5 is given to us. And finally, T2, apply n equals 2 to this equation, right? 2 to power 2 is 4, 4k1. Minus 2 to power 2 is also 4, plus 4k2. And simply k3 equals 15. Now, in some questions, it could be the case that you are not given the first three, so T0, T1, T2. Well, as the name implies, these are initial values. However, you could be given some other values. As long as you have 3, you are in the clear. Maybe you are given T1, T4, and T7. You can still plug n equals 1, n equals 4, n equals 7, and obtain 3 equations. Because you have 3 coefficients, you need 3 initial values. As long as you have 3, they don't have to be the very first 3. So T0, T1, T2, that is the usual case, but doesn't have to be. So now you have 3 equations in 3 unknowns, these 3 coefficients. What you need to do is solve this linear system of equations, which is not really that difficult. You can do it by hand if you like. You can use either substitution, or you can use Gaussian elimination, or maybe if you have access to a computer, you can use computing tools to find the solution of this system of linear equations. In this case, it turns out that k1 equals 2, k2 equals 1, k3 equals 3. Now, when you obtain the solution, I recommend, unless you use the computing tool, it's likely that you might make a mistake. Therefore, plug the values in these equations and see that they actually satisfy the set of equations, which I'm not going to do here, but you should be aware of what you have found. So when you have the coefficients, you actually have the solution, because those were the only things you needed. So put k1 equals 2 here, k2 equals 1 here, and k3 equals 3 here. Well, this is already 1, and therefore what you get is 2 times 2 to power n, which I write as 2 to the power n plus 1, plus, well, k2 is already 1, so I don't need to write it, plus minus 2 to power n, plus k3, which is 3. And this is the solution to this recurrence relation.